So if I have a reaction like O2 gas plus 4 ClO2 gas yields 2 Cl2O5 gas, and if I make the arrow not just going forward but also back, what this means is that this reaction is at equilibrium. The reactants have come together on the left to form products on the right, and now everything is everything. Nothing else is going on, but it's important to know that this reaction is reversible. So that comes into play later when we talk about shifting the equilibrium. For example, if I add more products, I could then sort of push the reaction back to the left. But for now, it's important to know that when you have arrow going forward above one going back, that this reaction is at equilibrium. And if we were to write it, let's say, a different way using variables, I'll say A plus B, which are my reactants. It's at equilibrium with C plus, well, in this case, it's just one product, but let's say if there was something else over there, let's say C plus D. And if I, let's say the coefficients I made lowercase, which are the numbers in front. Well, what I would have then is something like this if I want to write what's called an equilibrium expression, KEQ. Which basically says that I need to put the concentration of my products over the concentration of my reactants. And that's really all an equilibrium expression is. It's just a numerical representation of how much products you have in relation to how much reactants you have. Okay. And if I have, let's say, an equilibrium constant greater than 1, well, that means that I have more products. And this reaction will favor products. If I have one that's, let's say, less than 1 or a fraction, well, that would mean that I have more reactants. Why is that? Well, let's say I had a concentration of one product, 1 molar, whatever, over 3 molar reactants. And, you know, molar is going to cancel out. I'm just using some arbitrary numbers here. Well, this is less than 1. So this is going to favor reactants to have more reactants in the denominator. If I had a number greater than 1, let's say equilibrium constant or KEQ of, let's say, 1.5. Well, that's greater than 1, so that means that if I take a, let's say, 1.5 to 1 ratio, in other words, I have more products over reactants, then this is going to favor the products. If I had a number like, let's say, 50 for KEQ, well, if I turn that into fraction form, you get a 50 over 1, and that's going to favor products, anything greater than 1. Where if I have a fraction, again, let's say, I don't know, my concentration of products is 2 molar, or just some arbitrary number, over 20. Well, let's say have less products now, more reactants will favor reactants, right? So you get the point. So if I look at that a little bit more closely, what I'm going to have is this: that KEQ, or my equilibrium constant, or my equilibrium expression, is going to be the concentration of products, which if I break those down, it's going to be C, it's actually a bracket, times D, raising to the power of their coefficients. So concentration of C to the power of little c, concentration of D to the power of little d, over my reactants, or concentration of reactants rather, A times B, okay, and these guys up here. And I'm gonna have to raise them to the power of the coefficients, and that's how you get equilibrium expression. So, using that example of that first reaction we wrote at the start of the video, well, the KEQ is going to be this. K, or equilibrium constant, equals CO2O5 times, well, I don't have another product there, I just have one. Although I do need to raise it to the power of 2, because the coefficient was 2, right? Over concentration of my reactants. First one was O2 times ClO2 raised to the 4th power, since 4 was the coefficient. Yeah, in chemistry, brackets means concentration. And K, in this case at least, would be the same thing as saying equilibrium KEQ. Right. And if I were given specific concentrations or numerical values of these concentrations of products and reactants, I could get KEQ, and if it's greater than 1, I could tell you if the reaction is going to take place. Because that would mean that it would favor products if it's greater than 1. All right, let's try an example. Say you were given concentration of CO2O5 equals 3 molar. Concentration of oxygen gas is 2 molar. And the concentration of ClO2 is 1 molar. Okay. And we want to find equilibrium constant K for this reaction. And again, it's going back to our original reaction up here. Well, we've written our equilibrium expression. All we got to do now is plug in the values. So K equals concentration of CO2O5, well, that's 3. Right? And we have to square it, because remember the coefficient was 2, over 2 times 1 to the 4th power. So remember that coefficient was 4. And after we plug in the concentrations, we get 3 squared is 9, over 1 times 1 times 1 times 1 is 4. Actually, no, I'm sorry, that's 1. Anything times 1 is just 1. Times 2, that's going to be 2. And of course, you have 9 over 2, which equals 4.5. So if your KEQ is 4.5, you know it's going to favor products, right? Because it's greater than 1. And so this reaction will probably take place. Okay. So K equals 4.5. Which favors products.